Hello everyone, welcome to this lecture. In this lecture, we will continue our discussion over finite fields and we will focus in this lecture on the multiplicative group of a finite field and we will prove some nice properties regarding the multiplicative group of a finite field. Specifically, we show that it is always a cyclic group, it will have some generators and those generators are called as the primitive element, right. So, let f be a finite field with an abstract plus and dot operation and I denote by f star all the elements I denote by f star all to be the set consisting of all elements of the field except the 0 element, okay, where 0 is the additive identity element. And my claim here is that if I focus on the non-zero elements of the field and the dot operation, then that constitutes a cyclic group. Okay. And of course, it constitutes a group that comes from the properties of your field axioms, but what I am claiming here is that it is actually a cyclic group, and by cyclic group I mean that it has at least one generator. That means there exists at least one special element G or say F here such that all the different powers of f will give you the elements of the set f star. Okay. So, the proof strategy here will be the following. So, basically I want to show the following. Imagine that the non-zero elements are f1 to fn, there are n such elements. My goal is to show the following. I am claiming here that there exists at least one element f in this collection f star whose order is n. By that I mean that f to the power n is your identity element and n is the smallest such positive integer. Okay. If I can show that this claim is true, then that shows that indeed my set f star constitutes a cyclic group. It is already a group as I said, but if this claim is true, I end up showing that it is actually a cyclic group. Okay. And the proof is slightly involved. We will be taking help of several lemmas which are actually independent properties of groups and so on, and then we will finally arrive at the proof of this claim. So, the claim is actually proved by contradiction. So, we want to show that there exists at least one element in this collection f star whose order is n. The contradiction will be that there exists no element in the set f star whose order is n. That is a contradiction. If that is the case, then I have to arrive at some contradiction or some false statement. So, the proof strategy will be the following. I will be taking help of a simple fact regarding polynomials over the field. My fact here is the following. My claim is that if I take this degree n polynomial, which is a monic polynomial over the field, then it has exactly n roots in the field f. That is my fact 1. I can prove this very easily, but this is my fact. Actually, if you recall the properties of the roots of polynomials, we know that since the polynomial here is degree n, the number of roots can be at most n, but my fact here is that it has exactly n roots from the field f. And the proof of this fact is the following. My claim is that you take any element from the set f star, that means you take any non-zero element from the field f, it will satisfy this equation. If that is the case, then basically I am showing you that all the elements of set f star are the elements of the are actually the roots of this equation or roots of this polynomial. Okay. So, let us prove this fact that each element of the set f star is a root here. So, imagine that the order of the element f I is k. Okay. By that I mean that the number of distinct field elements which I can generate by computing different powers of F I is k, right. That is another equivalent definition of an order. Okay. That means F I power k is your identity element. Now, I can invoke here the Lagrange theorem of groups and subgroups. Now, since this cyclic subgroup F I is a subgroup of your parent group F star, of course, with the dot operation that I am not writing down separately. Then as per the Lagrange theorem, the order of F I or the order of cyclic subgroup F I generated by F I should divide the order of your parent group, and the order of the parent group is n, because as per my definition F star's cardinality is n. So, n is divisible by k, that means n can be written down as sum c times k. That means I can say that since F I power k is 1, then F I power n will give me the same element which I obtained by raising F I to the power c k. Then as per the rules of group exponentiation, I can take k inside and keep c outside, and F I power k as per the definition of group as per the definition of the order of F I will give me the identity element 1, and identity element 1 raised to power c will give me the identity element itself. That means, I have shown that F 1 is a root of x to the power n minus 1. I have shown that F 2 is also a root of the polynomial x to the power n minus 1, and f of n is also a root of the polynomial x to the power n minus 1. That means, I have shown you n roots. So, that shows that this fact is true. Now, coming back to this claim, I want to show that among the elements f 1 to f n there is at least one element whose order is n. I will show that if the order of none of the elements f 1 to f n is n, right, then I will show that this polynomial x to the power n minus 1 do not have n number of roots, but that will contradict fact number 1, because fact number 1 has been proved. I have established fact number 1. To prove this claim, my strategy will be to show that if there exists no element in the collection F star whose order is n, that means the order of F 1 is strictly less than n, order of F 2 is strictly less than n, and like that order of F n is also strictly less than n, then I will show that this polynomial does not have n number of roots, which will contradict my fact 1, and that will show that indeed this claim is correct. That is a proof strategy, but as I said, to prove this implication. So, now the proof boils down to proving this implication, assuming that the statement in the claim is incorrect. To prove this implication, I will take help of several lemmas, several related properties. So, let us prove those independent related properties. So, this is helping lemma number 1. So, here I want to prove some property regarding the Euler-Totent function denoted by phi function phi. So, recall that phi of n is basically the cardinality of the subset 1 to n, where the elements are co-prime to n. Basically, you want to focus on the number of elements in the range 1 to n which are co-prime to n. The number of such elements is denoted by phi of n. Now, we can prove a very nice property for this Euler-Totent function. The property here is that if you take various divisors here, so this notation d followed by slash and n, that means d divides n. So, the property here is that if you take various divisors of n, call them as d1, d2, dk and so on, and then take the summation of phi of those divisors, that will give you the number n. Okay. So, let us prove this. So, let S be my collection 1 to n, and imagine that d1, d2, dk, they are the distinct divisors of your n. Okay. Now, I am defining a collection C di. C sub di is basically all those elements from the set S whose GCD with n is di. Okay. So, what basically I am trying to do here is the following: if I take any number from the set S and try to find the GCD of that number x along with n, then the GCD has to be one of these divisors of n, because the GCD has to be first of all a divisor of n, and the only divisors of n are d1 or d2 or dk. So, that means if I take the GCD of any x here from the set S and the number n, it has to be either d1 or d2 or dk. So, I am basically trying to bucket or put all various elements of the set S according to the GCDs that they have with the element n. Okay, and the various buckets are C sub d1, C sub d2 and C sub dk. Okay. Now, as per the definition of this set C sub di, it is easy to see that this collection is actually a partition of S. It is easy to see that the disjoint of these sets is actually empty, because you can't have a number x whose GCD with n is both di as well as dj. So, that trivially shows that the intersection of these collections C sub d1, C sub d2 and C sub dk is empty, and it is also easy to see that if I take the union of various collections here, that will give me the entire set S, because you take any element x, either it will go to the bucket C sub d1 or it will go to the bucket C sub d2 or it will go to the bucket C sub dk, because if you take the GCD of x with n, it has to be either d1 or d2 or dk, right. A very simple fact here. That means, I can say that the summation of the cardinality of these individual buckets is nothing but the cardinality of your set S, and the cardinality of your set S is n. Now comes a very crucial claim. My claim here is that the cardinality of the bucket C sub di is same as the Euler-Toten function, the value of the Euler-Toten function for input n over di. And remember, n over di is a integer value, because n is divisible by di and di is a distinct divisor of n. Okay. Now, assuming for the moment this claim is true, okay, assume for the moment this claim is true, then if I apply this claim on this equation, so call this equation as equation number 1. If I apply this claim on equation number 1, I basically get that n is same as the summation of n, the Euler-Toten function for n over d1, the Euler-Toten function for n over d2, and like that the Euler-Toten function of n over dk. That is what I have written here. You take n is summation of various divisors of n, and then you sum over the Euler-Toten function for various n over d's. But now, if you see closely here, if you divide n by a divisor of n, you will obtain a divisor of n itself, right, because d1, d2, dk are the different divisors of n. So, if you divide n by one of the divisors, you will get another divisor. So, what I can say is, I can rewrite this equation and apply the logic that since d here runs through the various divisors of n, this n over d will run through those divisors itself. That means, whatever effect I can obtain here, the same effect I will obtain if I run through the divisors of n in this summation, and instead of taking the summation over phi of n over d, I simply take the summation over phi of the various divisors itself. Okay. Very simple fact here. So, for instance, okay, it is a very simple fact, I am not going to demonstrate, you can easily verify that. The proof for this is that since D is a one of the divisors of n, and if I divide n by one of those divisors, I will again obtain a divisor in the list D1 to Dk itself, right. And that shows, that proves my lemma, but now I have not yet proved this claim. So, this I have used this claim and then proved my lemma. Now, the question boils down to how exactly we prove this claim. So, my goal is now to prove that there are indeed these many number of elements in the ith bucket. So, for that let us try to analyze the property of each of the elements in the ith bucket. So, an element x will be present in the bucket C sub di if and only if the GCD of that number x and n is di, that is the definition of the ith bucket, right. But if the GCD of x and n is di, then that is possible if and only if the GCD of x over di and n over di is 1, very simple, right. Because if the GCD of x over di and n over di is not 1, then how at the first place the GCD of x and n was di. That means I can say that only those elements x will be present in the bucket C sub di such that for those x the GCD of x over di and n over di is 1. That means I can say that the ith bucket consists of all the elements in my collection 1 to n over di which are co-prime to n over di, because any number in the collection 1 to n over di which is co-prime to n over di, okay. So, call that number as x over di, you multiply that number with di, that will give you actually a number x which is having a GCD di with the element n. And how many elements I can have in the collection 1 to n over di which can be co-prime to n over di, as per my definition of the phi function, it will be phi of n over di, and that shows my claim is correct. So, I have proved my helping lemma number 1. My helping lemma number 2 is the following. Imagine I take a multiplicative group and imagine there is an element from the group G whose order is D. Okay, so, my element is x whose order is D. Then my claim is that for the same element x, if you consider the element x power k, and remember x power k as per the rules of group exponentiation is obtained by multiplying the x to itself k number of times, which will be an element of the group itself, because my group is a since G is a group, it satisfies the closure property with respect to the dot operation. So, the element x to the power k is actually an element from the group itself. Now, my claim here is that since x power k is an element of the group and it will have some order, its order will be d over GCD of d n k. Okay. So, to prove this statement, I will take the help of some property from the abstract group theory which we had discussed earlier. The property that I am going to use here is that if the element or x has order d, and then if you find that x to the power y is giving you the identity element, then that is possible if and only if the exponent y is a multiple of d. Okay. So, you can recall the proof of this fact from one of our earlier lecture. Now, my goal is to show that the order of x power k is this value, and for that we have to prove two things. The definition of order is you have to prove that if you indeed compute this power of the element x power k you will get the identity element, and that is trivial to prove, because since the order of x is d, that means x power d is the identity element, then I can say that the element x power k raised to this power will give you the identity element, right, because If I take x power k raised to power d over GCD of d and k, this is same as x power d whole raised to the power k over GCD of d and k, and x power d is the identity element. Identity element raised to power anything will give me the identity element, right. So, this is trivial. The second thing that we have to prove to show that indeed the order of element x power k is this is the following. I have to show that among all possible different positive powers of x to the power k, such that the sth power or the corresponding power gives you the identity element, the power where s is actually d over GCD of d over k is the minimum. So, what basically I am saying is that it is not the case that x to the power k raised to the power just single s gives you the identity element. There can be multiple exponents s. So, you can have an exponent s1 which gives you the identity element. You can have another exponent say s2 which also gives you the identity element, and like that you can have another exponent say Sn which also gives you the identity element. So, what I am basically trying to argue here is, in order to show that the order of x power k is this value, you have to show that among the various powers S1 to Sn, the power where the value of the power is d over GCD of d over k, d and k is the minimum one. Okay. So, the proof here is as follows. Since the order of x power k is s, assuming that s indeed is the order of x power k, I know that x power k s is 1, and if x power k s is 1, I can trigger this result regarding the order of x, and I can argue that k of s, k times s is a multiple of t. In the same way, k times s1 is also a multiple of d, k times s2 is also a multiple of d, k times sn is also a multiple of d. So, what basically I am arguing here is that if x power k and whole raised to power s1 is a giving you 1, that means k times s1 is a multiple of d, k times s2 is a multiple of d, and like that k times Sn is also a multiple of d, right. Now, I have to focus on the smallest Si such that the smallest k times Si which is a multiple of d satisfies the condition that x power k times Si is giving you the identity element 1. Okay. So, what I can say here is the following: if S is the smallest index or the smallest power among these various powers S1 to Sn, satisfying the condition that x power k times Si is 1, then the property of S is that S is the least positive integer of the form k times s, which is a multiple of d. That means, I can say that another property of the order s is that it is such that k times s is the least common multiple of both d and k. Of course, k times s is a multiple of k, right, but if at all, and k times s will be also a multiple of d, but since the order, since s is the order of element x power k, that means it is the smallest positive integer such that k times s constitutes a LCM or the least common multiple of d and k. Now, I can trigger or use the following relationship regarding the least common multiple and the GCD. If I take the LCM of d and k, that will be same as the product of the two numbers divided by their GCDs, and then I can rearrange the term. Since the LCM of d and k is k times s, I can substitute LHS by k times s, and then I get the conclusion that the smallest positive integer s such that x power k times s is identity element is actually this index. and that shows the helping lemma number 2 is also correct. And my third helping lemma is the following. The lemma says that if you have a multiplicative group and if you focus on all the elements of the group whose order is d for a given d, then the cardinality of E d will be phi of d if the set E d is non-empty. Of course, your set E d could be empty itself, that means there might be no element in the group whose order is d. The lemma says that if your set E d is non-empty, that means if there exists at least one element in the group whose order is d, then actually there are phi of d such number of elements. Okay. So, the proof will be as follows. We will take the help of helping lemma number 2, which we have just proved. So, imagine G is an element of the group whose order is indeed d. That means your set E d, E of d is not empty, and my goal is to show this property regarding the cardinality of the set E d. Since the order of G is d, that means I can say that the element G power d will give you the identity element. And now if you see closely here, each of these powers of the element G also will give you the identity element. Say for instance G power 2d, G power 2d can be rewritten as G power d and G power d raised to the power 2, G power d is 1. So, it will give 1 square and 1 square is 1. That means, if I take this polynomial x to the power d minus 1 over the group G, I have shown here that the elements G power 0, G power 1, G power d minus 1 are the distinct d roots of this polynomial x power d minus 1, and that is the maximum number of roots that I can have for this polynomial x power d minus 1, because this polynomial x power d minus 1 is of degree d. So, it can have at most d roots, but I have actually shown you d minus I have shown you actually d distinct elements from the group which constitutes the roots of this polynomial. Okay. That means, I can say that any root, right, you take any root of this polynomial, I can relate that root to the element G by saying that so say what I am saying is that if H is an abstract root, if H is any root of x power d minus 1, then I can say that H is either G power 0 or H is G power 1 or like that H is G power d minus 1, because I have shown that only roots which are possible for this polynomial are G power 0, G power 1, G power d minus 1. That means, one of these powers of G will give you the element H, where H is some root of the polynomial x power d minus 1. That is a relationship between any root of this polynomial and the element G that I have established. And what I also know is that you take any element whose order is d apart from G, right. So, you take any element say R such that order of R is also d, then whatever argument I have used here, I end up showing that element R also will be root of this polynomial, is not it, because if G has order d, then G constitutes a root of the polynomial x power d minus 1. In the same way, if R is a element different from G and his order is d as well, then R is also going to satisfy the polynomial x power d minus 1 and so on. But I already argued here that you take any root of the polynomial x power d minus 1, it is related to the element G, namely it has to be of the form either g power 0 or g power 1 or g power 2 or some g power k. So, tying these two properties together, right, this property and this property, I can come to the conclusion, following conclusion. If your goal is to find out various elements whose order is t, then it is equivalent to finding various elements of the form g power k whose order is t, because any element whose order is d will be a root of this polynomial, and if it is a root of this polynomial x power d minus 1, it will be of the form g power k, right. So, my goal was to find out the number of elements whose order is t. I have reduced that problem to another problem, namely finding the number of elements of the form g power k whose order is t. But my helping lemma 2 says that the order of the element g power k will be d over the GCD of k and d. So, when can it be possible that the order of g power k is precisely d? If your denominator becomes 1, namely if the GCD of k and d becomes 1, because if the GCD of k and d becomes 1, then I get that the order of g power k is d divided by 1, which will be 1. That means I can say that the number of elements of the form g power k whose order is t is such that actually equal to the number of elements of the form g power k such that the GCD of k and d is 1. And how many such k's can be there whose GCD with d will be 1? Well, there will be precisely phi of d number of such k values, and that shows that the number of elements in my collection E of d will be phi of d, right. So, coming back now to the proof of the main theorem which I wanted to prove. So, just to recall, I wanted to prove that if I focus on the non-zero elements of the field, it constitutes a cyclic group. Basically, I have to argue about the existence of a generator. I had already proved this fact, and these are my two helping lemmas which we had proved. The goal was to show that among the n elements in your collection f star, at least one element has order n. The proof will be by contradiction, namely we will show that if there exists no element in f star whose order is n, then this polynomial x power n minus 1 has less than n roots, and that will go against this fact number 1. So, let us prove this claim now. Assume that none of the elements from f star has order n. So, let the various orders which are possible, namely I have listed down the orders of various elements from your set f star, and let those orders be d1 to dk. Okay. So, you have n elements, it is not the case that all of them have distinct orders. It might be possible that order of f1 is same as order of f2, order of f3 and so on. Okay. So, it is not necessary that since you have n elements you have n distinct orders, few of the orders may be repeated. So, that is why let k be the possible orders for various elements in f star, and since I am assuming that there is no element in f star whose order is n, that means none of these orders d1 to dk is n. Okay. Now, I also know that each of these possible orders d1 to dk is a distinct divisor of n. Okay. They are distinct because they are the various possible distinct orders, and why it is a divisor of n? Because I know that the order of any element divides the order of any element from f star, which actually is a group, divides the order of f star, and the order of f star is n. So, that is why order of f1 will be divisor of n, order of f2 will be divisor of n, order of fn will be a divisor of n. Okay. Now, when I proved the fact number 1, I also argued, I also showed there that you take any element from f star, f1, f2, fn, each of them is a root of this polynomial, right. And as per our assumption that the order of f will be either d1 or d2 or dk and so on. So, by tying these two facts together, what I can say about the number of possible roots for this polynomial? The number of possible roots will be, namely the number of elements with order d1, the number of elements with order d2 and the number of elements with order dk. If I sum the number of elements with these orders, that will basically give me the number of roots for this polynomial x power n minus 1, right, because among the elements from f star, the orders that are possible are either d1 or d2 or dk, okay. And each element from f star is actually a root of x power n minus 1. So, that is why I get this equation. Now, I will use this helping lemma here, and I can say that the number of elements in f star whose order is d1 is nothing but phi of d1. In the same way, the number of elements from f star with order dk is nothing but phi of dk and so on. And what can I say about the summation in my RHS? The summation in the RHS is strictly less than n. Why it is strictly less than n? Because even though d1, d2, dk, they are distinct divisors of n, as per my assumption none of them is actually n. That means neither d1 is n nor d2 is n and so on. And as per the helping lemma 1, only when I sum over phi of various distinct divisors of n I will get the value n. But since none of these divisors d1, d2, dk is n, that means I am missing at least one distinct divisor of n, and that is why I can say that if I take the summation of these quantities phi of d1, phi of d2, phi of dk, I will not be getting the full n. If there would have been a divisor, if that means if I would have included phi of n here as well, then I can say that the summation of all these things is n. But since phi of n is missing here, because as per my assumption there is no number, no element from f star with order n, I can say that my RHS is actually strictly less than n, and my RHS is actually the number of roots of this polynomial. So, this goes against the fact 1, because I have separately shown already that indeed there are n number of elements from f which constitutes the root of this polynomial. In fact, all the elements of f star satisfy this polynomial, and that is possible only if at least one of the elements from f star has order n. Okay. So, that proves the theorem. So, now let us apply this theorem here. So, we have proved that you take any finite field, okay, and if you focus on the non-zero elements, we have shown it constitutes a cyclic group. That means the collection f star along with the dot operation will have a generator, and the generator is also called as the primitive element of your entire field. And how many such primitive elements will be there? You will have phi of cardinality of f star number of such primitive elements, because as per our helping lemma there are phi of d number of elements with order d. So, we basically want to find out how many elements are there with order same as the order of your f star. So, it will be same as phi of cardinality of f star. And now, if I apply this theorem for the special case of the field ZP, right. So, your ZP will have all the elements from 0 to p minus 1, and if I say ZP star, then it will have p minus 1 elements. So, all the elements except 0 are present here. If I since ZP constitutes a field If I focus on the non-zero elements, I get ZP star, and that shows if I apply this theorem, I get the conclusion that your ZP star is a cyclic group and it will have these many number of generators. And this is a very crucial property which, if you recall, we utilized during our discussion on Diffie-Hellman key exchange protocol and Elgamal encryption scheme. There we performed operations over ZP star, and there I assumed that it is a cyclic group with some generator. Right there you might be wondering what is a guarantee that indeed ZP star is a cyclic group. Well, now we have proved that indeed ZP star is a cyclic group and it will have many generators, it will have phi of p minus 1 number of generators. So, with that I conclude today's lecture. Just to summarize, today we discussed about the multiplicative group of a finite field, and we proved that it is a cyclic group. The generators of that cyclic group are also called as the primitive elements of your finite field. Thank you.